Jai Shri Gurudev. Dear students, today I'll be introducing you to an important topic in the second module. In the previous sessions, we have discussed about first module where you have learned a brief concepts on control system. That is, a brief introduction to control system was given along with classification, followed by we had taken the physical system in which you have learned about translational, rotational mechanical systems. Analysis of those two systems was taught to you. Now in this module, another important concept will be taught, named as block diagrams and signal flow graphs, which are very useful in analysis of many of the complex systems. So as the name indicates, a block diagram is nothing but a pictorial representation of a system, and signal flow graph shows you the flow of the values from one block to another block. So using these two representation, systems can be analyzed in an easier way. So in the second module, you are going to study in detail about analysis of systems using block diagram and signal flow graphs representation. So before studying this, you need to just know an important concept with respect to a system termed as transfer function. So in today's session, I'll be giving you a brief introduction about transfer function and how to analyze the system using the transfer functions. So let us get into this topic now. So transfer function, as it is shown here, it is a ratio of Laplace transform of the output to the Laplace transform of the input if you are analyzing your system in the S domain. So for example, if I am analyzing my system response in the Z domain, then it is taken as Z transform of the output to the Laplace transform of the Z transform of the input, that is in Z domain. Similarly, in the frequency domain also, you can consider a transfer function as a ratio of Fourier transform of the output to the Fourier transform of the input, considering all initial conditions to be 0. So in a simple way, if you want to define a transfer function, it is nothing but the transform of the output to the transform of the input. It could be either Laplace transform, or it could be a Z transform, or it could be Fourier transform. Whatever transform you want to consider, you can consider. But for the analysis of control system, we are going to consider Laplace transform here to identify the transfer function for a particular system. Now let us consider a plant like this, which is having an input as u of t and the output is taken as y of t. Okay, you know that plant is going to process your given input to generate a particular output. Now let's see how to find a transfer function for this particular system. Now if I am taking the Laplace transform for u of t, it is usually represented as u of s. Okay, in the S domain. Similarly, Laplace transform of y of t is represented as y of s. So here L represents the Laplace transform operator. Now if we take the Laplace transform for the input and the output for the given system, then the transfer function g of s is taken as y of s by u of s, that is ratio of Laplace transform of the output y by Laplace transform of the input u. So in the Laplace domain, the same system is represented like this, where g of s is considered as the transfer function for the system. So TF indicates that it is a transfer function for the system. So it is taken as y of s by u of s in this particular representation. So this is a simple definition of a transfer function, which is nothing but a ratio of output to ratio of input. Now we'll see why this transfer function is needed. What is the importance of this transfer function in the upcoming slides. Now generally a transfer function is represented with a differential equation like this, where if I am taking an input as x and the output as y, this is the differential equation, nth order differential equation representation of the system, whose transfer function is taken as Laplace transform of the output to Laplace transform of the input, which is nothing but an equation which could be represented in terms of s like this, where y of s by x of s is taken as b naught s to the power m, b1 s to the power m minus 1, etc. up to bm, where b naught to bm are nothing but your numerator coefficients, and a naught to an are considered as the denominator coefficient. So these two are called as the numerator. This is called as the numerator polynomial, and these are called as your denominator polynomials with respect to the transfer function. Now, why we are going to represent the transfer function using the polynomial representation like this is, if you factorize the numerator polynomials, you are going to get the location of your zeros. If you factorize the denominator polynomial, you are going to get the location of poles. I'll tell you what is the importance of these poles and zeros in the analysis of the system in the upcoming slides later. So I hope this is clear. Now coming to proper and improper transfer functions. Always one thing what we need to know is, when the order of the denominator polynomial, this one, is greater than the numerator polynomial, then the transfer function is said to be a proper transfer function. So this is one thing that need to be met. Otherwise it is considered to be improper. That means if the numerator polynomial is power is greater than the denominator polynomial power, then it is considered to be an improper transfer function which cannot be analyzed, and you need to convert into a proper transfer function, and then you can factorize and you can analyze the system. This is another important thing what you need to know with respect to transfer function polynomials, proper and improper. Now, what are the importance of this transfer function is, the transfer function for any system helps us to check the, first thing is stability of the system. So stability of the system, if you want to analyze, you need to know the transfer function for that particular system. And also transfer function helps us to find the characteristic of a system in time domain and frequency domain using suitable transformations. So this is another important aspect of transfer function, and the output response of a system can be found out using the given input by knowing the transfer function. Along with these things, we can also analyze the location of poles and zeros by factorizing the transfer function, which also helps us to analyze the stability of the system. So these are the three important main facts with respect to the transfer function. So any system can be analyzed using the transfer function. Okay. Now coming to stability of control system, there are several meanings for stability. So in general, when we define the stability for any system, we consider two types of stability, that is absolute stability and relative stability. Now what do you mean by these two things? Okay, see, stability of the system mainly, as I told you, it is represented by roots of the denominator polynomial and numerator polynomial, or factors you can consider. So roots of the denominator polynomial, as I told you in the previous slide, it gives us the location of what do we call it as poles. Okay, and similarly roots of the numerator polynomial of a transfer functions are called as zeros. Why the name is given like this is, see, poles, they have a tendency to take the response of a system towards infinity, and usually these are represented with a cross symbol. And zeros, they have a tendency to take the response of a system towards the value 0 or towards the origin. Hence they are represented, they are termed as zeros, and usually it is represented with the circle like this. So this is about poles and zeros. So this is what I told you in the previous slide. They are represented using this symbol, and zeros are represented using this symbol. And the system order is always equal to the number of poles of the transfer function. Very important thing. So if you want to determine the order of a system, it is nothing but equal to number of poles. So this is an example of an nth order plant with a transfer function where you have m poles and n zeros. Now coming to the stability of control system with respect to poles. So the poles are also defined as, it is a frequency at which system becomes infinite. That is what I told you. So system is going to tend towards the value infinity. So it is termed as at some particular frequency there is a tendency that the response of the system is going to become infinity. That is because of these poles. So hence the name pole is termed as a field where the value is infinite. This is what you mean by poles. Now coming to zeros. So 0 is the frequency at which the system takes the value as 0. So these are the two important things what you should know with respect to poles and zeros. Not only with respect to control system I'm talking with, generally it is for all the systems the same concept holds good. Now let's take an example and we'll analyze the system behavior. So let's consider a transfer function g of s as equal to x of s by y of s, which is equal to c divided by as plus 1. Now the denominator polynomial here is equal to what? As plus b, and if I'm equating it to 0, I'll get one pole at this particular location. So by equating the denominator polynomial to 0, I'll be getting the location of pole. Similarly, by equating the numerator polynomials, I'll be getting the location of my zeros. Here, since I've taken only one constant, there are no poles. And here, as you can see, we have one pole. Order of the system is nothing but equal to 1. This is a first order system. So order here is taken as equal to 1 for this particular example. So similarly, the power of s here in the denominator polynomial gives you the order of the system, or nothing but the number of poles in a transfer function gives you the order of the system. Now let's take few examples. So here we are considering a transfer function, and the task here is to find whether the given transfer function is proper or improper, then find the location of poles and zeros and the order of the system. Now as you can see here, in the first example, I have a polynomial s plus 3. Here in the denominator, I have the polynomial as s into s plus 2. If you can see directly here, the order of the polynomial in the denominator is 2 because you have two terms here, s. Okay, so here it is s plus 3. So the order of this particular system is taken as equal to 2. And coming to the number of poles here, what I have. So if I'm equating this to 0, s into s plus 2 equal to 0, you can just identify directly that one value what your s will take is 0. So s is equal to 0 and s is equal to minus 2. So that means I have two poles. These are nothing but your poles. Two poles at s is equal to 0 and s is equal to minus 2. Similarly, if I'm equating my numerator to 0, I'll be getting zeros. The zeros location as equal to s equal to minus 3 by equating the numerator to 0. So in this particular transfer function, I have one pole at location s equal to minus 3 and 1 0 at s equal to minus 3 and two poles at s is equal to 0 and minus 2. And the order of the system as told in the previous slides, it is equal to number of poles or the degree of your polynomial which is in the denominator. So the number of poles is equal to 2. So same thing holds good for the other examples which is there here also. So similarly, if you see the second example, we have g of s as equal to s divided by it is s plus 1 into s plus 2 into s plus 3. It is already factorized. So this shows as that we have 1 0 at the origin and 3 poles at s equal to minus 1, minus 2 and minus 3. And the order of the system is nothing but equal to 3. This is also considered to be a proper transfer function because here numerator power is, polynomial power is 1 and the denominator polynomial power is 3. And coming to third example, if you can see, the power of the numerator polynomial is 2 and the power of the denominator polynomial is 3. So that means this is also a proper polynomial or proper transfer function. So here we have two zeros at the same location. S plus 3 whole square means you will have two consecutive poles at the same location at s equal to minus 3. And here if you can see, we have three zeros, one at the origin and another one at S is equal to, in its imaginary value, you are going to get it as root 10 j plus or minus root 10 j. So that is the location of your poles. So your poles will be on the imaginary axis. Now coming to the last one, here in the denominator the power is 2 and in the numerator the power is 3. This is considered to be an improper transfer function. So here this is having 3 zeros and 2 poles. So 2 zeros at the origin and 1 zero at location s equal to minus 1, and we have 2 poles at s equal to 0 and s equal to minus 10. So this is how you can identify the number of poles, number of zeros, order, and you can check whether the transfer function is proper or improper. Now coming to the stability analysis of system using poles and zeros. The poles and zeros of the systems are plotted in the S-plane to check the stability of the system in this way. This is called as our S-plane. So this is called as left hand page and this is your right hand face. So here this is your real axis and this is your imaginary axis, and here S is considered to be a complex value which is represented in the form sigma plus j omega. Now if all the poles of the system, if they lie on the left half of the plane, that is if all your poles, if they are on LHP side, then the system is said to be stable. Or else if any one of the pole, if it comes towards your right side, then the system is said to be unstable. In some cases you will have poles here on the imaginary axis like here, then your system is said to be marginally stable. This is about stability analysis of the system using poles and zeros. If all the poles of the system here, if they are completely towards your left half plane, then it is said to be stable. So if among all the poles, if any one of the poles, if it comes towards your right half plane, then the system becomes unstable. So if the poles, if they lie on the imaginary axis, your system is said to be marginally stable. So that is what I told you here. This is called as your marginal stability. So here if you have, this is stable, this is called as instability. So this is very important with respect to analysis of the system with poles and zero locations. And coming to one more example, here let's take A is equal to 1 and B is equal to 3 and C is equal to 10. In that case, we have a pole at C, that is at minus 3. Okay, because B value I have taken it as minus 3. This is how you will mark the location of your pole on the axis in the S plane. So these are other few examples which I already explained. Now coming to another definition of stability, the system is said to be stable if for a bounded input the system produces a bounded output, that is known as BIBO stability. Bounded input, bounded output. So for any bounded input, if the output is also bounded or constant, then system is said to be stable. So if for example this is a unit step signal, if I am giving for a plant, and if this is your output what you are getting, then you have an overshoot in the response what you are getting, and system is said to be unstable in that particular case. So another definition of stability, if for any bounded input is not, if for example it produces an unbounded output, then the system is said to be unstable. So in the previous case, we have got a peak overshoot, but the response is coming to stability on some particular phase, right? But here in this particular example, even if I'm giving a stable input, my output is exponential. I don't know when it is going to reach the stability value as equal to 0. So this is an example of an unstable system. Now today I have given you a brief introduction about transfer function, how to find the transfer function for a system, and you have learned the definition of poles and zeros and how to find out the location of poles and zeros by using the given polynomial for a particular system, and you have learned how to find out the order of a system by knowing the number of poles, and along with that we have learned what is the importance of the transfer function and poles and zeros in the stability analysis of a system. So here you have learned about three important types of stability, that is absolute stability, marginal stability and relative stability. And based on these concepts, we are able to analyze the system whether it is stable or unstable. The one important concept what you need to remember in today's session is, if all the poles, if they lie towards the left half plane of your S domain, then system is said to be stable. If any one of the pole, if it is lying towards your right half plane of your S domain, then system is considered to be unstable. And if the poles, if they lie on the imaginary axis, then system is said to be marginally stable. So I hope all of you have followed today's concept, and these are the few references book which I have considered to prepare my presentation, which are nothing but your prescribed textbooks according to your syllabus. So you can go through these books for your remaining contents. I hope the session was interesting. Thank you one and all for your patience listening. Jai Shri Gurudev. I'm ending my session for today. Thank you all.